we need to do the air standard analysis of the V8 engine of Ferrari F8 Spider. All right. The temperature at the beginning of the compression process of the Otto cycle with a compression ratio of 9.62 is 300 Kelvin and 1 bar. So temperature at the beginning of the compression process is given. So P1 and T1 are given. Also what is given is the compression ratio, which is given as 9.62, okay, for this particular engine. Now the compression ratio is something that is a defining feature of the engine. If you're going to look at any other engine, of course the compression ratio is going to be different. And if you recall, we said the compression ratios are somewhere in the range of, let's say, 9 to 12. And we can approach higher compression ratios with when we are making use of a fuel with lower reactivity, like the octane 95 fuel. So as you can see, even for a amazingly fast car like a Ferrari, the compression ratio doesn't have to be around 12. It's about 9.6, reasonably high, but maybe could be higher in other cars as well. All right. So apart from this, we also have the cylinder volume, which is given as 488 centimeter cube. So this is basically the volume at state 1 or the Vmax, right? V1 is given as 488 centimeter cube. The maximum temperature during the cycle is given as 2000 Kelvin. Now, what does this temperature represent? What state it represents? We will see that once we draw the PV diagram. Okay, before that, it's really difficult to say what temperature it represents. Now, from common sense, you could probably say that it could possibly be the temperature at the end of the heat addition process, right? But yeah, once you draw it, we'll know exactly what number is that state. Is it state 2? Is it state 3 or what? Okay. All right. Now, just to complete this part about the Ferrari F8, this volume that I'm talking about here, this is the volume for one cylinder, right? So this car certainly has 8 cylinders as given by this V8 configuration. So it has basically 8 times 488 centimeter cube, or about 3.9 liter engine, and this is basically the capacity that's quoted on the cars when you look at it, right? So for example, if you're looking at a Camry, you will see maybe 2.4 liter or 2400 cc. Cc simply stands for cubic centimeter, right? So this indicates the cylinder volume of all the cylinders put together. Okay, so Camry typically comes with 4 cylinders, so we're talking about each cylinder having a volume of about 600 centimeter cube. All right, so this is how these all engines are sort of specified, with their displacement volume and also with the compression ratio. Although in the marketing material, companies tend to use this capacity a little bit more. So if you look at the marketing material for Ferrari F8, you'll see this number 3.9 liters somewhere. Okay, so here we need to do a couple of things. We need to determine the temperature and the pressure at the end of each process of the cycle. So we need to first remember what the processes are. We need to look at the thermal efficiency and then the mean effective pressure. Yes, Turki, go ahead.
Yes, Doctor, just wanted to ask the volume here for is it per a cylinder or for all the cylinders?
No, the volume here is for one cylinder.
Okay.
Yes. All right. So when you have this sort of a question, the first thing for you to decide, or the first decision that you're making, is to identify which sort of formulas to use for the isentropic processes, right? And whether you need to treat it as variable specific heat or a problem with constant specific heat. So here, since nothing is mentioned in the question about treating it as constant specific heat, so by default, we go with variable specific heats, which gives us the exact solution, right? So if nothing is mentioned, by default, you should select the variable specific heat option. Now, what happens when you select the variable specific heat option? Well, of course, you need to use this relative pressures and relative specific volumes to figure out the relations between pressure, specific volume, and temperature for different states, right? And we'll see how we make use of them. But the key part is to know that you're going to make use of this, all right? And of course, Another thing to remember is this applies only when you're dealing with isentropic processes. You can make use of it during the compression or the expansion process, which are both isentropic. You cannot certainly use this formula to relate the pressure ratios when you're looking at the heat addition or heat rejection processes. That simply is not correct. Okay. So the first thing is to identify what how to go ahead with this, and since nothing is mentioned about specific heats, or nothing is mentioned about constant specific heats, we can assume variable specific heats, right? Now, if the question had mentioned consider specific heats to be constant, of course we would not be taking variable specific heats. Another way to mention is they give you a specific value for the specific heat ratio, right? For example, they say consider specific heat ratio to be 1.4 throughout the cycle. Now, if they say this is basically telling you that you're treating specific heat to have one value throughout the entire cycle, which is an approximation and which basically tells you that you need to make use of constant specific heats, right? So this is something that you can pick and understand from the question itself. So again, by default, use variable specific heats. If you are not at all able to understand what to do, or I mean, in terms of selecting whether it's constant specific heats or variable specific heats, you can of course check with me. But yeah, this is a very straightforward method. You need to be clear on how to go ahead with that. Okay, and the homework problems that you're going to solve this week will also give you an idea about how to pick up or how to select specific heats in each of them. All right, so now let's go ahead and start looking at the PV diagram. So this is how the PV diagram looks like for an Otto cycle. As I mentioned before, this is something that you should be able to draw. Okay, this is not something you will be provided with, so you should know how to draw the PV diagram. You may also be asked to draw the PV diagram, maybe the TS diagram as well. So you should know how to draw both of them, or at least the PV diagram. Now, when we read this question here, again, we'll see that the temperature at the beginning of the compression process is 300 K and the pressure is 1 bar. So the compression process is 1 to 2. All right. So 1 to 2 is the compression process. So we know P1 and we know T1. The maximum temperature during the cycle is given as 2000 Kelvin. So here you can see that 1 to 2 is compression process, isentropic compression that is, and 2 to 3 is a constant volume heat addition. Now, of course, from this, it's very obvious that the maximum temperature during the cycle would occur at state 3, right? Because that's the state at which the heat addition has ended, and obviously you would expect the maximum temperature to be there. So T3 is given as 2000 Kelvin. And then 3 to 4 is an isentropic expansion process again, and you have constant heat rejection. So, of course, 4 cannot be Tmax, 2 cannot be Tmax. The only thing that can be where the maximum temperature will occur is T3. So again, this is something that that you need to draw the PV diagram to identify what state it corresponds to. All right, coming back, let's look at what's given to us. We have T1 and P1, but since we're dealing with an ideal gas, if you have T1, you can go ahead and determine the internal energy at state 1 and also VR1. Okay, so VR1 is 621.2. Again, these two are just functions of temperature. We have everything that we need for state 1, right? Now we need to determine the temperature and pressure for all of the states. So we need T2, P2, T3, P3, and so on. So the question is, how do we determine temperature at state 2 and pressure at state 2? So let's start with saying, how do we determine temperature at state 2? How do we go ahead with determining T2? All right, there's a lot of silence, so let me give you a hint. Well, what kind of process is the is happening from 1 to 2?
Is it a polytropic process?
Um, well,
Constant
it
volume.
it could be polytropic, but the process from 1 to 2 is the compression process, right? And constant volume heat addition is there, of course, from 2 to 3, but 1 to 2 is not a constant volume process. 1 to 2, you can see the specific volume is changing. 1 to 2 is basically an isentropic compression process, right? It's an isentropic process. And for isentropic processes, we can make use of the formula which relates the ratio of specific volumes to the ratio of volumes. So basically, when you're looking at an isentropic process for an ideal gas with variable specific heats, the ratio of volumes, or which is equal to the ratio of specific volumes for a closed system, will be equal to the ratio of the relative specific volumes, VR1 by VR2. Okay. Now, we already know the ratio of volumes, right? Which is basically the compression ratio. The compression ratio is Vmax by Vmin is the ratio of V1 to V2. Okay, this value is already given as 9.62. So basically, what we know is VR1 by VR2 is equal to 9.62. Now, if you recall, I already said that VR1 is going to be a function of only temperature at state 1, only a function of T1. And we already found it from table A22. Okay, so we have the value of VR1. We have the value for the ratio of VR1 by VR2, which is 9.62. So we can easily plug in these numbers and determine the value of VR2. So VR2 would simply be VR1 by 9.62. VR1 is 621.2 as we found from the table. So VR2 is 64.57. Now, once you have this VR2, the beauty of this ideal gas is that the specific volume, the relative specific volume, is only a function of temperature. It depends only on temperature. Okay, so if you know this, you can go to the table and determine the temperature at which you get this values, right? So you go to table A22 and look up the different values of VR. You will see that a VR of 64.57, it corresponds to a temperature of T2 of 720 Kelvin. Okay, about 720 Kelvin. It's actually, if I recall correctly, 720.1 or 720.2 maybe. So it's fair to approximate it as 720 Kelvin. So this is how we get T2. Okay, you got to make use of the fact that the process from 1 to 2 is an isentropic process, and of course make use of the variable specific heat. How do we get that? Well, of course, this is how we know, right? So these formulas are given in your formula sheet. So we knew that for variable specific heats, the ratios of specific volumes are equal to the ratios of relative specific volumes. So that's how you make use of it. Okay, so that's T2 obtained. We also need P2, right? We said pressure and temperature at the end of each state. So how do we determine P2?
Would we use the relation PV equal RC?
Right. We can make use of the ideal gas equation. So basically, from the ideal gas equation, you have the ratio of pressure, volume, and temperature to be constant, right? So you can write either PV is equal to RT, where V is the specific volume, or you could write pressure times volume is MRT, right? So we're dealing with a closed system. The mass is going to remain constant. The R is going to remain constant. So basically, PV by T is constant, or you can write it as P2 V2 by T2 is equal to P1 V1 by T1, right? It's an ideal gas at all states. So this ratio has to remain constant, and it's going to be equal as you go along every different state. Okay, so now we need to determine P2. We have the value of T2. T1 was given in the question, and we already know the ratio of V1 to V2, right? And what is the ratio of V1 to V2?
9.62.
Exactly. It's given in the question, right? It's the compression ratio. So now it's just a matter of plugging in the numbers again, right? So P1 is 1 bar, again given in the question. V1 by V2 is the compression ratio, given in the question again, provided you know what it stands for. And then T2 by T1. T2 is something we just calculated. So this comes out to be 23.1 bar. Okay, so the pressure at the end of the compression stage is 23.1 bar. Now, I want you to consider a situation. right? So here we said the compression ratio is 9.62. R is 9.62. Now, let's say I want to increase the thermal efficiency of this engine a bit more. Okay, so if I want to increase the thermal efficiency, what should I do with what should I do to P2? Should I increase P2 or should I decrease P2? Now, everyone who says I should increase P2, uh, please raise your hand. I want to increase the thermal efficiency. So the question is, should I increase P2 or should I decrease it? For now, all those guys who says I want to increase P2, raise your hand. Okay, six. Six of you say we need to increase P2 to increase thermal efficiency. All right, seven. Okay. Now, how about the remaining guys? Do you think we need to reduce P2? How now? Okay, we'll do this voting again. Everyone who thinks we need to reduce the pressure at stage two, we need to reduce P2 to increase thermal efficiency. Please raise your hand.
I think we should increase it.
Okay. So we have about four guys who are saying, well, okay, that's a total of 10 people. What about the remaining 22? You don't have an opinion or you don't want to say? Look, guys, I want participation, right? So it does not matter whether you're right or wrong. The thing is, when you do this, that's when you're going to understand what's happening. So let's discuss both solutions. We had about 6 to 7 people saying you need to increase P2 to increase thermal efficiency. Can one of you explain why do you think so? Why should we do that?
We will increase the pressure because it will lead to increasing the temperature, which
Mhm.
means increasing the denominator. Since the thermal efficiency is 1 minus TL divided by TH, so that's why I said increasing the pressure.
Okay, makes sense. That's good. Any other explanation? Okay,
The same, doctor.
all right. Yep. Thank you both. How about the guys who said P2 should be reduced? Why do you think P2 should be reduced to increase thermal efficiency again? Okay. Looks like everyone is happy with the explanation Turkey gave. Well, actually, that explanation is correct one, right? So if you want to increase the thermal efficiency, we actually would have to increase the pressure at state two, and basically you'll also need to increase the compression ratio, right? Once you increase the compression ratio, the pressure at state two would be higher, and we would be compressing a gas a little bit more. And the simple reason is um, we want to increase P2 to increase thermal efficiency, because when you increase P2, as Turkey says, you're increasing the temperature of heat addition, right? You're increasing T2. So if you recall, the efficiency formula for Otto cycle is 1 minus T1 by T2. So if you're increasing T2, well, of course, this term becomes smaller and the thermal efficiency goes up, right? So this is simply what's happening here. And I mean, there are several explanations to it, but this is the simplest explanation. So if you want to increase the thermal efficiency of this Ferrari F8 Spider, you got to increase the compression ratio. 9.6 is good, but maybe you can push it to maybe, I don't know, 10 or something like that. And the P2 would correspondingly increase maybe to 30 bar or something. So if you are given the task of increasing the thermal efficiency of the Ferrari engine, well, this is one option. Okay. All right. It's great. I hope things are clear to everyone. And for those of you who answered the pressure should be reduced, well, the thing is, at this stage, things are not so clear to us, right? It's not you cannot just look at the engine and it's not very obvious that okay, this is what you need to do to increase the efficiency or uh, what exactly how do we approach increasing the thermal efficiency is not very clear. That's the whole reason why we bother about doing an analysis, right? A simple analysis to start off with to give us a better idea about what are the parameters, right? So just by looking at it, we could think that okay, maybe I should reduce P2 a little bit. That'll reduce my work input during the compression process, something like that, right? There could be um, several ideas on why you thought reduction of P2 would make sense. But the thing is, yes, we do the analysis just to understand what actually helps, right? If everyone understood without doing any analysis, we would not be needing this. So you don't have to be disheartened. It's the important part is, I guess, everyone understands now why we need to increase the pressure to improve thermal efficiency. Anyway, so that's all done. We have temperature at state 2 and the pressure at state 2. We can, of course, go ahead and determine the internal energies at this state and also the VR2, which we already know. So now the question is about state 3. How do we go ahead and determine the required conditions at state 3? Well, T3 is already known because we sort of looked at the PV diagram and we figured out that the maximum temperature during the cycle happens at state 3. So T3 is 2000 Kelvin. The question is, how do we determine P3?
Can we find it using isentropic equation?
Okay. Yes, we could have certainly used the isentropic relation relating two different pressures, right? Let's say P2 by P1 raised to maybe the temperatures. But for this to happen, we need to uh, deal with a process where entropy is zero. So entropy is zero only during the compression and the expansion processes. So from 2 to 3, sadly, it's a constant volume process, right? Constant volume heat addition process. The entropy at state 2 is not equal to the entropy of state 3. So we cannot make use of that, right? So that's the only thing we need to be looking for. So yes, we can make use of it during the process 1 to 2 and 3 to 4, but we cannot make use of it during the process 2 to 3 or 4 to 1. So this is another important thing why we need to draw this diagram and be clear on what processes are isentropic and what is not. So yes, we cannot make use of that sadly, but there are other ways of doing it. Any other ideas? Well, it's not very complicated. We just have to make use of the ideal gas equation again, right? 2 to 3 is a constant volume process, right? So V2 is equal to V3. And we said for an ideal gas, we can always write this equation, right? So PV by T is a constant for all states. So just like we said, P1 V1 by T1 is equal to P2 V2 by T2. Of course, the gas is remaining ideal gas throughout, right? So P2 V2 by T2 should also be equal to P3 V3 by T3. Mustafa, you want to add something?
I have a question, Doctor.
Yes.
You said that this question we can always use it in the gas. If it is for isentropic process or for all ideal gases.
This is the ideal gas equation. It applies for all ideal gases at all states, all processes.
Okay. Okay.
All right. So here, of course, the volume is remaining constant from 2 to 3. So you can just cancel out the V2 and V3 part. And all we are left with is with the pressures and temperatures, right? So we already know P2. We know T3 given in the question. T2 is something we calculated. So now we can calculate P3 directly. It comes out to be about 64.2 bar. Okay. So we have done this for the three states, 1, 2, and 3. Now the way we are going to determine the pressure and temperature at state 4 is very similar to what we did for determining the pressure and temperature at state 2, provided the values at state 1, right? 1 to 2 and 3 to 4 are isentropic processes. So this is the place where we can make use of those relative pressures, relative specific volumes and stuff, right? So since 3 to 4 is an isentropic process, again, we can relate the ratio of specific volumes to the ratio of relative specific volumes given by this R, right? VR4 by VR3. Now, we don't know V4 by V3, it's not given in the question, but we know that V4 is equal to V1, right? Here, V1 is equal to V4 and V2 is equal to V3. Both are constant volume processes. So you can sort of replace V1 with V4, V2 with V3, and again, this ratio is something that we know now, okay? And it's the compression ratio as given in the question. VR3 is just a function of temperature, so you can get it from the table A22, okay? So here determining VR4 would simply be equal to 9.62 times VR3. VR3 is known, so you plug that in and you get 26.7. Now this is what we have. Now VR4 is only just a function of temperature. So if you can go back to table A22 and look up the different temperatures and figure out at which temperature the VR value is given as 26.7. You have to do some interpolation, but you'll see that it's very much it matches with 980 Kelvin. I think since it matches with 980 Kelvin, you don't need interpolation, but sometimes you may need interpolation if it was something like 982, 983 or something like that, right? So here we are lucky we don't need to do any interpolation. So the T4 comes out to be 980. Now, once you have T4, well, you can go ahead and determine the value of internal energy as well. We're going to make use of this a little bit later. But we have T4. Determining P4 is very straightforward. We can again make use of the ideal gas equation, right? And V1 and V4 is same. So you can just it just comes out to be the ratio of temperatures, just like what happened for the process 2 to 3. Okay, so once you do for the processes 1 to 2 and 2 to 3, you're going to make use of the same methods to determine from 3 to 4 and 4 to 1. Okay, so we have T4, we have T1, we have P1. Just plug those numbers in and you get P4. Okay, so with this, we have determined the pressures and temperatures at all stages, right? From at all states. So P1 to P4, T1 to T4. Now, this was part A of the problem. We need to go ahead and determine the thermal efficiency. Now, determining thermal efficiency here is pretty straightforward, right? We can make use of the formula, the net work done in the cycle divided by Qn. Now, you have two options. Either you could actually calculate the net work done during the cycle, which is work out during the process 3 to 4 minus work in during the process compression process 1 to 2. You could do this, or you could just make use of the formula 1 minus Q out by Qn. Okay, it's your choice. I'm going to show using both of this, right? We'll use the formula for the net work in the cycle when we calculate the mean effective pressure. So for now, you can make use of the formula 1 minus Q out by Qn because this is a simpler way of doing it. Now again here, when you apply the energy balance to this process 4 to 1, okay, so you're gonna get Q out as U4 minus U1 and Qn as U3 minus U2. Now, why is this internal energy? Why not enthalpy here? Why are we getting internal energy from the balance, from the energy balance?
Because
Because
it's a
it's closed
constant
system.
volume.
Okay, can you guys say one by one?
A closed system.
Okay, Abdul Hamid, what do you want to say?
A constant volume.
All right. Actually, you know, yes, it's a constant volume process, and thanks for responding. But the correct answer is the fact that it's a closed system, because even if it was a, a sort of, I mean, a process where you're having constant volume, but it was not a closed system, then you would have to take enthalpies because there could be some flow involved with it, right? So since it's a closed system, from the energy balance we're going to make use of, we'll be getting internal energies. You get enthalpies primarily when you're dealing with open systems. Now there is a special case where we also look at enthalpy differences, which is what happens when you're looking at the work done in a constant pressure heating process, but that is just an exception to it. But whenever you're looking at closed systems, the internal energy change is what you're looking at. Okay, And that's because that's what primarily happens. In your open system, we also have to deal with flow work, which appears as PV. So you have U plus PV, which is why we look at enthalpies. All right, so here, since we are not dealing with constant specific heats, we are dealing with variable specific heat. So you got to pick up these values directly from the table A22. Okay, we have all these values here because we had the temperatures. So U4, U1, U3, and U2, you plug those numbers in and you get the efficiency. It comes out to be about 54.1%. All right. So here the main part was actually determining the temperatures and pressures at different for all of these different processes. Once you had that, going ahead and calculating thermal efficiency is pretty straightforward. Okay, you know this formula, right? 1 minus Q out by Q1 is something we're going to use so frequently that you already know it. All right, so once this is done, the last part is to determine the mean effective pressure. Now, mean effective pressure is some sort of an average pressure. Okay, it does not represent any pressure within the cycle. It's an average pressure indicating the work output per unit volume of the cycle, right? So this is sort of something that's used to compare different engines. So the formula for mean effective pressure is net work output of the cycle divided by V1 minus V2. Okay, the Vmax minus Vmin, the displacement volume, that is. Now, you have two options to evaluate the work done within the cycle, right? You can either take it as work done during the expansion process 3 to 4, that is U3 minus U4, minus the work input during the compression process, which is 1 to 2, so which is U2 minus U1. Or you could also write it as Q out minus Qn. Sorry, Qn minus Q out. Okay. It's the same thing, right? It's going to give you the same values. So Qn minus Q out is also equal to the work done in the cycle, the net work done. So either way you can do it. Here I'm showing you using the other method. And here for the thermal efficiency, we use the Q out and Qn thing. All right, so here there are again multiple ways to do it. I could also determine the mass and then make use of the volumes. But just to make things simple, what I'm going to do is I'm going to calculate the work done in the cycle per unit mass. So the work done per unit mass is basically what is the change in the internal energies. Otherwise, I would have to multiply the mass here. And here, since I'm dividing by mass, I need to also divide the volume by mass, right? So when you divide the volume per unit mass, it's going to become specific volume. So V1 minus V2. So here I could just take V1 common and I'll have 1 minus V2 by V1, which is just an inverse of the compression ratio. So it's 1 by 9.62. Okay, so how do we determine V1? Well, you just get it from the ideal gas equation, right? It's RT1 by P1. The only thing you got to be careful here is to put the temperature in Kelvin, which you would do probably because the temperature is given already in Kelvin here. You don't have to change anything. You just have to be careful to use the pressure in kilopascal. Okay, so here the units of R, the universal the gas constant for air, it'll be in kilojoule per kilogram Kelvin. So you got to make sure that you put things in kilopascal, the pressure in kilopascal, that is. You don't put 1 bar here. It's going to give you a wrong answer. So once you do this, this is what you get, 0.86 meter cube per kilogram. So that's the specific volume. So for calculating the MEP, we have everything now. We have the U's at 4 different states. We have the specific volume at state 1, and we have the ratio. Okay, you can just plug them in. And of course, when you do that, the pressure that you get again is in kilopascal. And the simple reason why that appears in kilopascal is because of the consistency of units, right? The internal energy is in kilojoule per kilogram, and you're having kilogram per meter cube here for the density. Okay, so what you're going to get is in kilopascal, but in the question, we need to provide the answer in bars. You just need to divide it by 100 and you get it in bars. So it's 8.08 bar.